Section 8.1, we're looking at parabolas today with our conic sections. Even though the parabolas are listed in the first section and seem like they should be the conic section that we would be the most familiar with since you've been using parabolas all the way back in Algebra 1 already, the structure is a little bit different in terms of the formula than the rest of the conic sections, which is why we're saving this one for our last conic section. To create the parabola out of the cone, you see how we're taking this plane and slicing it at an angle here. Just looking at the top half of that parabola looks kind of like the same type of curve that you saw in the hyperbola, except for this was a vertical plane that was going through. Now we have this plane going here at an angle to create that parabola. The analytic definition, we've seen an analytic definition for all the rest of the conic sections, and the parabola, no different. The parabola is the set of all points in a plane that are equal distance from a particular line, which is known as the directrix, and a particular point, which is known as the focus in the plane. So let's take a look at this picture and we'll point out each of those elements. So the first thing that we want to mention is that you notice we do not have a center of the parabola like we had a center of the circle, the ellipse, and the hyperbola. So the parabola does not have a center. The parabola has a focus, but just one, right? All the other shapes had two foci. Now we have just one focus point, and we have just one vertex point. And so when we talk about our parabolas to start, we're going to look at parabolas that have a vertex at 0, 0. This vertex of the parabola has the same function as the center of the other shapes. And so that becomes a little bit tricky because we're used to the center being the middle and then everything based around that. Now the vertex point is where everything is based around. So we have our vertex point of the parabola. That's our minimum point right here. That focus, just like the hyperbola wrapped around the focus point, you see the blue parabola here is wrapping around this focus point as well. In chapter 2, we had talked about the axis of symmetry. You see this red dotted line, which is our axis or axis of symmetry of that parabola. That axis crosses directly through the vertex, and you notice that the vertex is in line with the focus, and so this axis of symmetry goes through both the focus and the vertex. We also have another line known as the directrix. So you see this horizontal line of the directrix down here. The horizontal line of the directrix is perpendicular to the axis of symmetry, so that's creating a right angle down here. And the definition here telling us that the parabola is a set of all points equal distance from a particular line, the directrix, and a particular point, the focus, in the plane. So you notice the example they're giving you here, they're picking this point on the parabola, and what they're telling us is if I draw a line from the focus to the point on the parabola, and then another line from the point on the parabola down to the directrix, creating another right angle there. These two lines are exactly the same length. And that would be true no matter which point on the parabola that I would pick. So let's say that I pick this point right here. If I draw a line from the focus to the parabola and then parabola back down to the directrix, those two lines should be exactly the same length. Now, what that also means for us is if I pick the vertex, the point from the focus to the point on the parabola, that's the vertex right there, and from the point on the parabola down to the directrix should also be the same length. So this line right here and this line right here should be the same exact length. So focus to vertex, vertex down to the directrix, exactly the same distance. So let's do a little more labeling on our parabola as we talk about the structure. When we look at this parabola, we're going to assume that our vertex here is at 0, 0. Remember the vertex taking on the qualities of the center of the other conic sections that we looked at. So we're going to have this vertex here at 0, 0. And when we do our labeling here, we've got our focus. We don't have any A's, B's, or C's when we're talking about the parabola. Again, different than the rest of the conic sections because really we just have this focus and the directrix and the axis of symmetry. And so what they use as we talk about the parabola is the letter P. And so we're going to say that we have a distance of P going up, and we have a distance of P then, remembering that this is the same distance down to the directrix. So P up to the focus, P down to the directrix. So if you're going to label that focus point, that means that coordinate going up a distance of P is 0P. And that means going down to the directrix, if I was going to label this point, now that point isn't really anything in particular or on the parabola, but what this point tells me, if this is the coordinate 0, negative P, and then this directrix is a horizontal line, that means what's the equation of the directrix? It's a horizontal line, so that's a y equals equation. It's crossing through negative P, so that's going to help tell me that this is the line y equals negative P. So we have the focus, we go up a distance of P to that, we go down a distance of P to get to the directrix, so that line is currently y equals negative P. And then we also have our axis of symmetry. And in our axis of symmetry, in this case, it's a vertical line, so that's going to be an x equals equation. Looks like that axis is crossing through x equals 0. So x equals 0 is going to be my equation for the axis of symmetry. We'll talk about the equation of this parabola in just a little bit, but a couple other things for us to notice about this. As you now see on the top of the screen, P is the distance between the vertex and the focus. We just talked about that. If the P value is negative, what is that going to mean? That's going to make this graph open downward. And the last thing is something called the focal width. The focal width is the absolute value of 4 times P. What is the focal width of the graph? That focal width value, 4 times P, is a line that is perpendicular to the axis of symmetry and crosses through the focus point. So if I draw something perpendicular to the axis of symmetry, I guess that's going to make that parallel to the directrix, if I can draw a straight line here. So this purple dotted line is indicating your focal width. So that value is essentially going to tell you how wide or how narrow your parabola is, because if your 4P has a distance of 4 versus the 4P having a distance of 12, a focal width of 12 is going to be a much wider parabola than a focal width of 4. All right, and the next thing that we want to know is the equation. Well, wait a second. Let's think about what you knew about a parabola just back in Algebra 1. If I said, what's the basic equation of this parabola, I'm pretty sure you would be able to tell me, hey, I know parabolas are y equals x squared. Keep that in mind. That's going to help you to remember all of these equations as we move through. Our general equation with a vertex at 0, 0 of our parabola would be y equals x squared. But like we said, we know this focal width could change. We sometimes have parabolas that are pretty narrow. We sometimes have parabolas that are much wider. And so how are we going to adjust for that? The equation that we end up with for these parabolas then turns out to be y equals, and I just need to adjust this coefficient. Instead of just an x squared, I'm going to put a coefficient of 1 divided by 4p. So my equation of my parabola is y equals 1 over 4p times x squared. So when we look at this next slide, again, seeing up in the upper right-hand corner our equation, y equals 1 over 4p times x squared. As we said, if that p value is positive, that's going to give you a nice parabola that's opening upward. Then you see that your directrix was at y equals negative p. If that p value is negative, now your parabola would open downward. And that would make sense to us because we know if I had something like y equals negative 2x squared, we've seen equations like that. A negative number in the front just flips that parabola upside down. So that seems to make sense. The other thing I want to point out to you is the top of this slide shows you how the textbook writes the equation. X squared equals 4p times y. They write it in that format, I think, because they're solving for the x squared. However, I've found through the years that it seems like people are a little more comfortable with our y equals x squared equation. We've been using that for a long time. And so all this equation does is say, now we just need to deal with what that coefficient is. So I just want you to note that when you look at this in the textbook, they might write their equations in this format. It's obviously equivalent just by dividing that 4p over to the other side. So I just want you to be comfortable with the equation. I'm going to write everything in this format, y equals 1 over 4p times x squared. If you choose to write it in the format of the textbook, that's okay. You can do that as well. Now, just like our other shapes had an option of changing where the major axis was or the transverse axis, our parabola also has an option of changing that as well. And so we know that y equals x squared is a parabola that opens upward, but we might also see a parabola that instead opens to the side, to the right and to the left. If that happens, it's just a slight change in our equation. Check out the upper right again. X equals 1 over 4p times y squared. So now it's the y value that's squared, and the x is just raised to the first. Everything else is the same, and you have 1 over 4p as your leading coefficient. The same properties hold true, that the focal width is the line that crosses through the focus and is perpendicular to the axis of symmetry. The focal width is the absolute value of 4 times p. If the p-value is positive, this parabola is going to open to the right. If the p-value is negative, now this parabola is going to open to the left. And p is still the distance from the vertex to the focus and from the vertex to the directrix. So it's just a matter of your axis of symmetry now being a horizontal line and your directrix being a vertical line instead of the reverse of that. Parabolas are all over the place, and you're going to see a couple examples in your homework as well. When you look at the satellite dish that you see there, when you look at this guy, you might have seen something like this when you watch football on TV. There's a parabolic shape inside there, and it has to do with the focus. Look at the focus right here on that satellite dish. Inside of this object, you've got a focus inside there that's collecting all of the sound. So the focus happens in a lot of cases. You'll see some homework examples with a flashlight as well, where you're talking about where is that focus going to be, because that's going to collect everything. Everything is based around that point. So that should give you the information that you need for the structure of the parabola, and you will move on to the homework examples. They're going to be broken up into 2 different sections. You're going to start the homework examples with problems that do not require completing of the square, and then you'll do a second section where you then look at the examples where completing the square is needed. The completing the square in the parabola, again, just slightly different from what you've seen in the other conic sections, because now your parabola only has 1 squared variable instead of 2.